The next talk is about AI and diffusion models by Ruba Haroun. Ruba is a research engineer at Google DeepMind, specializing in diffusion models for media generation. Previously, her research focused on efficient model design for transformers. Ruba is also experienced in reward modeling for LLMs and code generation. Welcome.
Thank you for the introduction.
This is the clicker for the users.
Okay. Hi, everyone. Do you hear me well? Hi, I'm Ruba Haroun. As Safa said, I'm a senior research engineer at Google DeepMind, and I work in the Gemini team. Specifically, my research interest is diffusion models for media generation, image generation, music generation, and before that I worked on efficient alternatives for transformer, which is the main architecture used for LLMs. And yeah, I've also done a bit of research on reward modeling and code generation. And today I'll be talking to you about diffusion models. Just by show of hands, who have heard of the term diffusion models before? Oh, wow, that's amazing. Okay, so this hopefully can go very quickly then. Okay, so I split the talk today into 5 different segments. So first of all, I'll talk about useful generative modeling concepts that we'll build the talk on. And then I'll talk a bit about iterative refinement, which is the main paradigm for generative modeling. And then we'll take an intuitive look at diffusion models. Obviously, diffusion models is a very complex and dense topic. We'll try to keep it as math-free as possible and give just a high level about why they work the way they are and how they work, actually, and the intuition behind them. And then we're going to talk about guidance as one of the very powerful tools that make diffusion models very efficient and better for practical applications. And the last part, I'll talk about latent diffusion and some bits and pieces that don't fit into any of those segments. I'll just briefly go through them at the end. I don't think we can do, given the size of the group, I don't think we can do questions in the middle of the talk, but hopefully we'll have some time to answer some questions at the end. Otherwise, I'll also be around, so feel free to just come to me and we can talk. Okay, so generative modeling. Okay, so we assume that we have some set of data that comes from an underlying distribution, P of X, and that's the distribution we want to model. This is the distribution of interest. And when I say we want to model distribution, we want to create a neural network that will produce samples that look very similar to the true data set that we trained this model on. And there are a few ways we can do this. One taxonomy that I like is explicit versus implicit models. And in explicit models, we take P of X and we parameterize it, and you fit a model to model this P of X using your true data set, basically. And the key idea here is that your neural network outputs a probability distribution, and you sample from that probability distribution. So you're calculating P of X using your neural network, or approximating P of X using your neural network. While for implicit models, you don't calculate P of X, but instead you construct a scheme where you input some noise and get a sample immediately. So you don't do the sampling yourself, but your neural network will produce a sample for you. So you don't have a mechanism of scoring the likelihood of these samples. You just get samples, while with explicit models, you can actually score sequences. One example of that is LLMs. For example, if you have a sequence, you can compute the probability of the sequence under your sets of weight or under your theta params. And another useful concept that I want to discuss is conditioning. Basically, a conditional generative model is a model that produces a conditional distribution rather than an unconditional one. Very trivial. So instead of modeling P of X, you're modeling P of X given C. And C is a conditioning signal or a control signal. So you can use it to control what type of samples you get out of your model. And it can be anything, basically. It can be, for example, if you're building a conditional model of ImageNet, you can input a label, and you get an image that corresponds to that label. Another thing, you can also input grayscale images, and you get a probability distribution of all the color images that can be an outcome of colorizing this grayscale image. And the reason we output a probability distribution is just to account for the uncertainty and the ambiguity, because there is a large set of images that can be the colored version of this image. So instead of just producing one image, you produce a probability distribution, and then you sample from that to get one instance of these colored images. And I've kind of put them in a scale where the arrow here represents the density of the conditioning signal that you're using. And you can measure that in bits, basically. When it's a class, then it's a very small signal. And when it's an image, then obviously the density of the information you're providing is higher. OK. Let's talk now about iterative refinement. And the premise of iterative refinement is that you start with a canvas of what your sample should look like. And I think my screen went. OK, it's back. Sorry. Yeah, iterative refinement. You start with a canvas, and your neural network gets applied multiple times to shape that sample into a data point that looks similar to your training data set. And there are two classes that fit into this paradigm. There is autoregressive models, and then there is diffusion models. And in autoregression, you take your data points from your data set, and you serialize them, you convert them into 1D sequences, and then you generate a sample step by step or a token by token. I think most of the people here are familiar with LLMs and the mechanism of sampling from LLMs. And the other class of model that is iterative refiner is diffusion models. And here you basically start with a 2D canvas of what your image look like, and you basically iteratively find and shape this canvas into a real image. And you do that by learning a denoiser during training. So you apply noise to your real data, and you learn to gradually remove that noise from your images. And then one natural question you might ask is, can we use autoregressive models to model images? And yes, we can, and we'll go into the pros and cons of using diffusion model versus autoregressive models for image generation. I'll just give 2 points here about autoregressive models from a probabilistic perspective. When we are trying to model X, where X is a sequence of tokens or a sequence of pixels, what we do is that we factorize this probability distribution into a product of conditional probability distribution, P of X given X, Xi's. And basically, this is basically what's the probability of the current token given everything that I've generated before. And we use the same model at each step or at each token we're producing. And we can apply this directly to pixels to generate images. So what we can do is that we can flatten our images into sequence of pixels, and we can autoregressively generate pixels by pixels. And this has been a focus area for a lot of work. For example, there is Pixel RNN and Pixel CNN that autoregressively generate images. But there are a few issues with this approach in the context of image generation itself. The first thing is the main assumption that the data set have a 1D structure, which is not the case for images or videos or media in general. For images specifically, the inductive bias is that our data set have like very strong 2D structure, which is something that the autoregressive models don't turn to model or respect very well. And the other thing is that the problem with autoregression is that you kind of like overcommit to tokens that you produce. So if you make an error, you can't correct that error in later samples from the model. While with diffusion, because you're working with a 2D canvas and you're refining that canvas progressively during sampling, even if you make mistakes, you can then correct those mistakes as you sample. So that's why, at an intuitive level, why diffusion models just fits the inductive biases of images better than autoregression. And then, yeah, you can also apply autoregression to generate audio as well. So something like WaveNet, where you just serialize audio waveforms and then predict them bit by bit. OK, now we get to the main point, which is diffusion models. I think I've already spoke about the idea of iterative denoising here. And if I want people to focus on one slide to just like get a gist of what diffusion models are and why they are formulated the way they are, it would be this slide. And I want to start by just painting a picture. Think of your P of X that we spoke about, which is the probability of your images or natural images, as very complex high-dimensional probability distribution. And the reason it's very high-dimensional is because every channel of each pixel is one axis of this probability distribution. So even for lower resolution images, that could be like hundreds of thousands of dimensions, or even millions of dimensions. And this high-dimensional probability distribution is also super complex and has a lot of modes. So even if you try or you train a model on this probability distribution to model this probability distribution, it would be hard to sample from it because it would be hard to cover all the different modes. And you can think of modes as regions in this high-dimensional space where your true images exist. For example, there could be a mode that corresponds to images of cats, and there could be a mode that corresponds to images of dogs, and so on. These are just examples. Obviously, you can't draw these kind of conclusions about high-dimensional space, but the point is there are modes, and they exist in high-dimensional space, and if you want to sample from that distribution, it will be very hard to cover all these modes and move between them to produce images that are trade-off between the two. On the other hand, we have simple probability distributions like the Gaussian distribution, where it has a single mode and it's relatively easy to sample from. So what we're doing with the diffusion model is that we'll try to learn a mapping from this simple probability distribution to that complex high-dimensional probability distribution. And our neural network will guide us into how to go from samples from this small, dumb, or simple distribution to real samples from our data, if that makes sense. And we don't do this in one step. We don't go just from like an image or a canvas of Gaussian noise to a real image directly. Instead, because that would be a very difficult learning process. But instead, what we do is we go gradually by applying noise to our images and learning to invert that noise step by step. And that's basically how we map from a simple distribution to a complex distribution. And I think that kind of like would summarize the whole idea of diffusion models. Sorry? 5 minutes? OK. All right, so I'm using a few notations here. So x0, in this case, is the clean image from your data set. And x infinity is basically the outcome of applying multiple stages of noise to this image. And as you see, as you go to the right, you're slowly destroying the structure and the information in the images. And your model will learn to put these information back. And why do we use Gaussian noise? Because it has, or why do we like sample our noise from a Gaussian distribution? Because it has nice properties. One of them is additivity. So basically, if you combine, if you add smaller increments of Gaussian noise, that would be an equivalent. That would be equivalent of adding just one larger Gaussian noise. So instead of doing the process of noising your images step by step, what you can do is that you can use this property to skip to any point in time in our diffusion process. So you can go from x0 to any point in your diffusion process in just one step instead of tediously doing it sequentially or in a for loop. And another practical thing we do is that we don't go to infinity. So we go to a fixed time t, and in the original DDPM paper, that t was 1,000 steps. So we take 1,000 steps of noising the image, and we arrive at something that is not Gaussian distribution, but it's simple enough to sample from. compared to our image distribution. And then another practical choice that we make is not only do we add noise, we also scale down the magnitude of the input a little bit by multiplying x0 with alpha t. And the reason we do this is just to stabilize training, because if you incrementally add multiple noises to an input, what happens is that the standard deviation of your activation will increase as a result of that until it explodes, basically, which is really terrible for stability of your model training. So what we do is that we scale down the activations a little bit. It also helps that all of your inputs, I'm pretty sure all of you are familiar with normalization, where we ensure that the magnitude of our activation remain the same during training. So we do the same trick here. So no matter what xt, no matter where we are in our forward process, our noising process, we make sure that the standard deviation is kind of the same as like different time or different noising stages. So this is the forward process, and then I'll skip this part, but I guess I'll say one point about this. The choice of sigma t, you can think about it as the noise schedule, which controls the intensity of the noise we apply at any time t, and it increases monotonically with time. So for smaller t's, the noise is very small, and we're just destroying the texture of the image, but for larger t's, we're completely destroying the image and transforming it into a noise, basically. And then there are multiple formulations for alpha, for scaling down the input. One of them is various preserving, and in summary, this is basically if your input has a standard deviation of 1, if you're operating with a standardized input, this choice of alpha will maintain all of the noisy versions of this input to have a standard deviation of 1 as well. There is also variance exploding formulation where you set alpha to 1, which is basically accepting that the variance will explode, so you're not scaling down things. And the reason why this is okay to do is that we don't go to infinity anyway, so we don't add infinite noise. We stop at a time step t, and maybe it's fine. We know that the variance will increase, but we know it's not going to explode. So in these settings, it's okay to allow the variance to explode. And then there is another formulation, which is a very popular one, rectified flow. But I also can't go into details about this. Okay, so this is the forward process. Let's talk about the backward process, which is basically how do we sample from this denoiser. So to summarize training, you sample a data point from your data set, you sample a time step, you apply a noise that is proportional to that time step to your clean input, and then because you know how much noise that you've added, you can force your network to remove that noise. So you can get your neural network to output a prediction of what the noise that was added, and then you minimize the distance between the true noise that you added and the prediction of your network. So effectively, you're training a denoiser that goes from a noisy image to slightly less noisy image and so forth. For the backward process, I want to start with kind of like a geometric visualization of what happens. So you start from xt, which is during sampling, it's just a white canvas, it's random noise. And then you ask your neural network to make a prediction of what the clean version of this input is. So you ask it to denoise that image. And then you take, basically the output of your network is not the true image, it's a direction that you should move to clean up this image. So you take a step into that direction. And the reason why this is the case is that because when you're starting with noise, there are multiple options of what could be the slightly less noisy image that gave rise to this image. So your model will not predict a specific image, it will predict an average of all these possible images. So you don't go all the way there, or you don't basically treat the prediction of your network as the clean image, but instead you treat it as a direction in your image space, or like a centroid of a subpart of your image space. And you take a step in that direction. And then you add some noise to this prediction. And the reason we add some noise, I know it's counterintuitive, because if we're trying to remove noise using our model, why do we add noise again? And I guess the point of adding noise here is to account for the approximation error, because your neural network will make mistakes because it's not a perfect approximator of the denoiser. So what you do is that you add some noise to kind of robustify this algorithm a little bit. So even if you make mistakes in your prediction, you account for those by adding a bit of noise. And then you take another prediction of your model. So now that you've denoised the image a little bit, you're not done yet, right? Because you still have a noisy image, because you still haven't arrived to X0. So you do this process over and over again until you arrive at a clean image. One thing that is worth noting is that as your image gets cleaner and less noisy, your model's predictions are going to point you to a smaller subspace of your data distribution. Because now you have less noise, the set of possible images that are producing this image will shrink, basically. It will get smaller and smaller and smaller. So you can kind of anneal the process of adding noise to your prediction. So at the beginning of sampling, you add a lot of noise, but then as you get closer to the clean image, you reduce the amount of noise that you add. Yeah, and then you do this process over and over until you're satisfied with the quality of the images produced by the diffusion model. I think I'm going to skip this part, but this is basically talking about what is the formulation of the loss function you use. You can predict basically X0 directly from XT, or you can predict the noise, or you can predict a linear combination of the two. All of these predictions, how you parameterize your neural network, are equivalent because you have a closed form equation here that will map any of these to the clean image. So it doesn't matter ultimately what you're choosing to predict was your model, as long as you can arrive at X0 from that. Okay. One last thing that I wanted to talk about is guidance, which is a really powerful tool to make diffusion models produce really high quality images. It's actually one of the most important tricks we apply in practice. And the way that I like to think about it is guidance is like a cheat code that allows diffusion models to punch above their weight. So even if you have a small diffusion model, you can get images of superior quality from that diffusion model that are similar to quality that you'll get from an otherwise larger model by just using guidance. And the whole idea of guidance is that you basically have a classifier. Think of any image classification model off the shelf. I forgot to mention that guidance is an inference trick. It's not a training trick. So we apply it at sampling time only. But basically, what we're doing is we're incorporating some signal of a classifier in addition to the signal we're getting from our denoiser. So a classifier will give you the probability, the log probability of a specific class label given an input. And what we can do is that we can get the gradient of that classifier with respect to the input, which is basically how do I change my input so that I'm maximizing the probability of this class label. So how do I change this input so it looks more bunny-like, basically, in this case. And then we have this basically log probability or gradient to update our input. And then we have the input from our denoiser, which tells us basically how to move this XT, how to denoise this XT and move it to be more realistic under our data distribution. And then we don't just go in the direction of the denoiser. We take a middle ground between the two, between the conditional path and the unconditional path. And so we end up with an image that looks like bunny, but is also super real. And that's the idea of the classifier guidance. And here I've included a slide about the Bayesian perspective that governs this whole process. It's not just something we decided to do. There is a Bayesian formulation that you can follow. And do I have time to go through this real quickly? 2 minutes. Okay, so basically your classifier is P, C given X, and then this is your conditional probability distribution, and then you have your unconditional probability distribution, and then your P of X given C is using just Bayes' rule is proportionate to the product of the two. And if you take the log of this equation, you can account for this proportionality by a constant C. And then if you take the gradient of that, you basically end up canceling out C because C is a constant, so you end up with the grad log probability of the classifier prediction plus the grad log of P of X, which is the two vectors that we summed in the previous slide. So one of them is how do I change my image to look more bunny, and then the other one is how do I change my image to be less noisy or more real. One problem with classifier guidance is that because we use it at inference time, we feed the classifier model noisy images, which it might not have been trained explicitly to handle. So you might get some noisy classification as a result. So that's one of the drawbacks of using classifier guidance. One last thing that we apply also here is that you don't have to just sum the two gradients. You can add a knob to tune basically or control how faithful you want to be to this class label, or how faithful do you want to be to your classifier gradient. And this is the guidance scale over here. We multiply the log prob of the classifier with the scale, and we sum that up to the denoising gradient we get. And in the probability sense, this is equivalent to raising the probability distribution of the conditional classifier to a power of this scale, basically. Yeah. And to mitigate the problem of these off-the-shelf classifiers not accounting for noisy inputs, what we use in practice is actually not classifier guidance. What we use is classifier-free guidance, where in summary, instead of relying on an external model to learn or like fine-tuning a classifier on noisy images as well, what we do is that we use the same model that we use to denoise. We use it also to produce a conditional probability distribution. During training, we split our time between modeling P of X, the unconditional branch, and also the conditional branch, which is P of X given C. And this is just whether you provide the prompt, for example, or the class label or not. So 20% of the time, for example, we provide the class label of an image, and 80% of the time we drop it. So effectively, we're learning both the conditional and the unconditional probability distribution. And then at sampling time, we basically apply the feed-forward twice, one with the class label and one without, and we take basically a step in the diff between those two vectors. So we amplify the difference between the two, and we move our prediction into that direction. And again, there is like a Bayes formula that governs this process, but we can't go through it as well. But anyways, I mentioned before that classifier guidance is a way that we can also like trade off model quality for diversity. So when you introduce these conditional probabilities, you're kind of narrowing this subset of images that you can produce. So you get less quality, less diversity of your model, but you get a lot higher quality images. So these are examples from the GLIDE paper, which is the first OpenAI paper that does diffusion models for pixels. And on the left-hand side, you see when you don't apply a lot of guidance. And on the right-hand side, you scale up the guidance that you use. And you can see that while there is a lot of diversity on the left-hand side, the images generally look poor in quality. And on the right-hand side, you don't see any diversity. But if I would have to pick an image to represent this prompt, then I'm more likely to choose an image from the right just because of the quality. And then this is another example of that. Yeah, and then the last point, the last section of our talk is we actually also don't apply diffusion in pixel space, we apply diffusion in latent space. So we learn an autoencoder that produces latents for our images, and we apply the same forward and backward process that we talked about in that latent space. And there are different reasons why we do this. One of them is just efficiency purpose, because latents usually are lower dimensional compared to pixels. And because sampling from diffusion models is actually super expensive because you apply the network over and over again to refine the predictions, and you also apply twice per a time step to get the conditional and the unconditional branch. So it's worthwhile doing this process in a slightly compressed tensors. So that's why we use latents for practicality reason. The other reason is just from a perceptual point or from a modeling point. And the reason here is that images have like different frequency information in their composition. So you have informations like texture, and you have informations like composition, and these have like different frequencies in images. And if you kind of abstract away the low-level information into just one latent space, then that's probably more efficient for your diffusion model to model, basically. And you have also like different realism versus the diversity trade-offs that you care about at different perceptual level. For example, for low-frequency information, you don't care about you care more about reality than you care about diversity. For example, you care that the composition, the image of a dog, or like the structure of what a dog look like, you care about it being realistic rather than diverse. And then the opposite is true for structure. For example, if you ask for an image of a landscape of grass, you don't care about the diversity of this glass, you also care about the realism of it. So constructing a latent space of a way is a way of abstracting away all of these differences between the different perceptual levels in images. And the way we do this is that we split our diffusion overall training into two different parts. So first we train the autoencoder with a combination of 3 losses: regression, perceptual, and adversarial. And the thing we care about in this stage is that we get high quality latents that we can reconstruct through images from. And then in the second stage, we train the diffusion model on these latents. So we freeze the encoder, and we learn the denoiser on these latents instead of pixels. And during sampling time, we bring back the decoder, because the output of our sampling time is going to be denoised latents, and we use a decoder to invert those latents back into pixel space. And I think this is like a summary of what is the current framework for doing diffusion models. And I'm gonna skip. And yeah, last part is I've included some samples from some of the famous image generation model, Imagine4 and Imagine3, and also Nano Banana, which is another application of diffusion models for image editing and text to image. Yeah, thank you.